Yes, you can focus on how you're doing the calculations, how we're thinking about structuring that possible problem with how we have clustering or we don't have well-defined properties. But even though we're doing that, the key is it's not changing the estimates. That's not the big thing. You can get it in terms of helping in terms of inference, but it's not really, shouldn't be the overall commanding issue within any type of research. It's meant to be something that just, helps you improve how you discuss and you go about inference. So this is where we're going to sort of adjust a little bit from what we've done so far. So far, everything that we've done is referred to as conditional mean estimates. What we get in terms of OLS, or we do have other what we refer to as conditional mean estimators. In that case, what we're doing is we're looking at the global or the global average or the mean of the conditional distribution, looking at the average effect across that sample. Now, a lot of times, basically, that's interesting. It's not saying that you should jump to any other estimate that allows the heterogeneity. But by allowing or trying to look at that, it does give us a little bit more information. It allows us to be a little bit more maybe specific about the relationship between groups or how we're looking at this variation. Or do we make sure that, that should we actually be looking at the average if we're looking at, say, programs that are supposed to help low-income families? Is the average really what we want to see in that case? We might want to look at other portions of the conditional distribution. Doesn't mean that we have to jump to this, because we can see that by using maybe some type of binary variable that allows us to see it within our regression sets. But there are other methods out there we might want to look at. So looking at the conditional mean, what we're doing, basically a lot of the work, no matter what we do, large portions of what we do in economics, always is focused on the mean. Well, not always, sorry. Large portion is focused on the mean. There are types of concepts or estimators that allow us to look at the conditional mean. So, but that's just one point on the conditional distribution. The mean is still important. No matter what I say after this, it's important. It's a global measure. Okay? It is influenced by, if you want to hunt for outliers, or how the distribution is in terms of, it's not really normal, but there's a long right tail, we have skewness, those are all going to be affected. But that is the distribution. To say it's wrong, that you're claiming a lot there. It is giving us information, but we can look at other areas of the conditional distribution, or a lot of different areas of the conditional distribution, depending on how we go about it. So another reason we stick with those is these models are well developed. Simple interpretations, easy to provide information to whoever we're talking to or trying to convey our results to. So that's why anything, like I said, anything I say from now on, I'm not saying go to this type of modeling. I'm just saying that it's a different option for you. But the standard or the base is typically these conditional mean models. So why look for more? Basically, we can look for heterogeneity. We've already done that with our interactions. We're starting, basically, as soon as we can start to see differences within our sample due to characteristics, for allowing for variation with other variables, we're basically starting to look for heterogeneity, or starting to find, not look, but find it. So we've used interactions already. Some things we haven't shown but you could show are looking at random coefficient models. We allow random disturbances to sort of affect, and we can actually model that over observations as options. Or we can even rely on different ways of setting up similar models, but just a slight tweak on how we think about the left-hand side variables. Those kind of fall into what we refer to as margin. So you find this in labor and you find this in international trade, where we focus on the first, the extensive margin that looks at whether or not you perform an action. Do I work or not? Once that is chosen or determined within a particular model, then we can actually look at the next step. Of those who are working, how much do you work? Or if you're looking at trade, once you determine whether or not a pair trade, then we go to the next step of how much you trade. Those are two different questions. And it does provide a way of looking at heterogeneity. Okay? But again, they're all focused on one thing. So the question in terms of the first one, whether you trade or not, is binary. Basically, so it's still about trade. It's just about the first step. I make a choice. If I make the one, then I can say, how much do you do of it? So it's still about heterogeneity. But these are all ways of doing similar types of ways of seeing that variation. Okay? So there is more applied researchers are using what we're going to refer to as the conditional quantile regressions. Now, I'm going to focus on the conditional quantile because basically it's what most likely one of you might use. There are other ones called unconditional quantile regressions, but it's a different type of question. Okay? So just make sure that, and the thing is, in the last 10 years or so, this area has been sort of exploding in terms of what modeling strategies we use. And sometimes it's going so fast that people are actually using models that it wasn't meant to be used in that way, and they're actually possibly using it the wrong way. That's sort of why I wanted to go in this. If you go into this area, make sure that one, you're using the proper way and you're discussing it in the proper way so that you don't fall into that. I don't want to say they're using it wrong. It's just that it might be, well, no, it is wrong. Let me just say it that way. So just keep that in mind. That this area is like getting very wide, especially if you're in just the cross section. It's a little bit more standardized. It's not as bad. Once you get into the panel realm, it gets it's varied on basically the situation of the data structure. And those techniques cannot go across all the types that we have. So that's why I'm saying it's very varied, because it's basically reliant on sort of data structure, assumptions, a lot of different things. That's why I'm sticking just to the basic here. You see the big warning sign I'm putting, right? Don't say that I said that you could use this. It's very particular sometimes, and the discussion needs to be very particular on how you go about discussing it. So this is a generalization. Do not take this as like a, what do you call it? That is always true. This is a generalization. I actually took this from one of my papers because basically we put it there just because in our area nobody really uses quantile, so we need to see in general how things are sort of handled. If I show this to an econometrician, they would say no, 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 because there's certain assumptions going on here. But this is, like I said, a generalization. So this is, like I said, the quantile regressions are expanding very quickly. The research is going in very many different directions. But in general, when we're looking at linear regressions, we're thinking that our outcomes under under good conditions are basically predictions of the conditional mean. We often assume normality, even if we know that's not true. And I haven't really probably mentioned that today, but even in the case of wages, we don't consider that being normal. Not because it's any way skewed, but because there is a cutoff at 0. When we think continuous, that's negative infinity to infinity. This one has a boundary to it. So in that way, we don't really think of it being normal. Then we take the log, we get something that's more normal, but at the same time, we've removed anybody that's at that cutoff. So again, we've made a choice to throw them out, which is selection on our part. So we get into a big headache. Also, when it comes to preservation in terms of the Jensen inequality that I was talking about before, the expectation of the log is not equal to the log of the expectation. That is true for most models that we're looking at it like this. It's also sensitive outliers. It does apply to small n for the most part, as long as all the properties are met. And then we have, for the most part, the best part is that most programs can run it like that. Doesn't matter how many observations, it's easy to run. Okay. When it comes to quantile, we're going to be looking at a different portion of the conditional distribution depending on what quantile we choose. We choose the median, then everything that we're going to get is going to be the answer we're getting is relative to that localized outcome in terms of the median. We're looking at the 75th percentile, we're looking at that localized area. Okay? And the good thing about it is, especially from what you're going to learn in terms of when we're doing logits and probits, we can actually, in some ways, be agnostic about the distribution. We're assuming that we don't know the distribution, but we don't actually need to know it. Now, if you talk to someone else, you will note that basically the way you set up your model, you actually would be, in some ways, implicitly assuming what it is. But in general, this is what they say, so that's the way I'll keep it for now. Now, when it comes to transformations, it doesn't fall under the Jensen inequality because it's not. We're looking at the quantile. When we actually log it, in the quantile, we're ordering out our dependent variable. When we log it, that order remains the same. It does not change. Since it's ordinal like that, we don't have to worry about our transformations. If we do our estimation in logs, we can actually transform it back easily into whatever the unlogged is. So something I didn't say earlier is a lot of times we estimate log wages. You take that to your boss for some type of policy analysis they want to do. He's going to say, who cares about logs? I need to know what the effect is on wages, not on logs. So that becomes a little bit more difficult when we're thinking about this problem. In quantiles, not so much, as long as it meets some very nice properties in terms of the data. In most cases, remember I said it's a localized outcome, so it's not going to be as responsive to outliers. Basically, we need sufficient data. So in this case, it needs large N in some cases. Again, to put a number on it is kind of hard. It depends on the actual field that you're in. The biggest problem is it is computationally intensive. It will put stress on your CPU. Okay? These are not standard type outcomes. So a lot of times we're basically doing a linear programming model. There is no way of doing it in terms of calculus. Basically, we're forced to go through the methods that we have. In this case, it's a linear program. They're not quite easy to run. Now, the programs that we use for this, they do it for us. But at the same time, they do take a while to run. So the larger your data set gets, the longer it takes. More covariates that you're actually using to explain why, it's going to put more and more time in terms of actually calculating this. So I'm trying to tell you the good and the bad. And sometimes the bad outweighs what you can get out of the good of it, okay? Otherwise, sometimes not so. So just balance those two things in your mind before you attempt to do it. Okay, so a lot of times this is what you would like for what you're kind of looking at in terms of your data. You know, it might be something nice and neat, and we have some type of, you might be able to put it as a normal distribution for the most part, or at least something like it. And in terms of the quantiles, it's nice because our median is falling roughly where our mean is at. So it's, It's nice in that sense. But in some cases, we have something that is bimodal. It's a little bit harder to put. Apparently, I had something at the bottom there that I need to adjust. But basically, in that case, we know that that mean and median are not going to fall in that same area. Okay? This is one of those things where we're going to get a very different answer from what we get from the conditional mean model versus sort of what we get from our quantile regressions. Or we should. I'm not saying we definitely should. Sometimes the results are very similar, even in this kind of case, because overall it's just focused on the localized versus the global. So until we get to the estimations, just, think that basically it can be giving us different information. So I'm not going to go through a lot of the theory. Like I said, I'm going to try to focus just on the intuition. Now, these models have been around for a while. In 1978, Conker and Bassett basically just sort of set the foundational work for the CQR. And again, I'm not speaking about the unconditional. I'm only thinking about the conditional. In this case, there are a lot of new techniques, but at the same time, because this actually isn't taught in almost any graduate course or econometrics course, understanding it can be quite, there's some papers that have been put out that basically misinterpret what's coming out of the quantile regressions. So I didn't want to go into all of those, but the WINS 2019 is a very good overview of how we think about this. Because one of the things that we typically do, and you might not even notice this, whenever we run OLS, we say that the effect on education is, say, 7%. Technically, what you're getting out of that result is a conditional mean. But through iterative expectations, we can basically push that back into the unconditional, saying this is the effect at the unconditional. Now, in this case, this is on the conditional. That means we can only say conditional on our right-hand side variables, this is the effect. We can't push that back into the unconditional from that. If that's the case, you can't just say, this is the effect, say, at the 30th percentile. And because some of my population that are at 30th percentile saying that this is the effect on them, they're not guaranteed to be at that position in the conditional. They could be at the other side because we're conditioning on all these effects. So we have to make sure that we stick to discussing this as the conditional effect, not the effect on the population, which would some people push for being the unconditional effect. Okay, so keep that in mind when we're doing this. We still speak about them in the same way, but we always make sure that we focus, say, this is the conditional effect on whatever regressor we're looking at. When it comes to the mean conditional, sorry, I put this as mean regression. I probably should have told you. So this is what we're typically thinking about. In terms of the conditional, we're thinking about this tau as being something that we can condition on. It is not only the variables, the x's that we're looking at, is actually we're conditioning on which quantile we want to look at. And if most people would focus on, the 10th, 20th, 30th, and so forth, or you could go for every quantile from 1 to 99, or you could go from, 0.001, 0.002. There are hundreds, thousands. You could basically try to get all this. Most people don't go that route, but basically some type of good fine grain type of granular analysis of the quantiles is usually what we do, at least at maybe the 5th, 10th, 15th, or at least the 10th, 20th. Something that tells us that it's not a wide range when we're looking at this. But that means that in this one, we're getting one answer. Here, if we're doing, the 10th, 20th, and so forth, then what we're getting is 10. Or sorry, in this case, 9. But that's 9 answers to the 1. But that's one answer for each portion of the conditional quantile. Okay? And that's why we have to make sure that whatever beta we have is specific to that tau. And that also includes the error term. So that's why it's a little confusing. You're not estimating one model anymore. However many quantiles you're looking at is how many models you are actually modeling. Okay, so it becomes a little bit more complex than what you've done in the past. Each of those is giving their own beta, and they're given their own error structure. So basically, just keep that in mind that it's not just one outcome. You can do it. Some people do compare the conditional median to what we get at the mean, and that's fine. But a lot of times we also want to see the other portions of it. So basically, one of the things that we do, so here we're assuming that strict isogeneity holds. Well, we sort of have to do the same thing for each quantile that we're modeling as well. So even though they say that it's giving more information, it's also making us assume a lot more information. The more assumptions we make, it can be a little bit more tricky in making sure that we're getting the proper answer. Remember, the more assumptions we add on, it's less, sometimes that can make it a little bit harder to sort of, that these properties are actually holding. Because here we're only looking at one versus a few different ones here because of that last one. So this is just going to be similar to the conditional zero conditional mean outcome. So say here 19 quantiles, this condition or zero conditional outcome needs to hold for all 19 of them if we're going to say that it's unbiased. So basically, can we compare the mean regression with the CQR? Both have different objective functions and properties, but applied researchers do compare the partial effects. Okay, not saying you can't, but you also have to take into account, or at least be upfront, that these are modeling two different objective functions. They're different properties. Yes?
As much as you give us some insight regarding the quantile, I'm thinking, since I'm dealing with current data, and I'm thinking of, like, to say, what if I decide to combine the conditional quantile regression model with the structural equation model, whereby I'm looking about 6 pillars. 6 pillars being smart economy as a variable, smart governance as a variable, smart environment as a variable, smart mobility as a variable, smart society as a variable, and smart living as a variable. Mind you that I would use formal data to try and maneuver around piece together. I don't know whether this kind of models is capable of.
Are you saying as each of those is a dependent variable?
Independent.
Oh, those are the
Independent.
as long as they're not changing over, as long as you're using the full data set. So the one thing you need to keep in mind here, even though we're only at, say, the median, right? We're not only including variables that are, we're including the entire data set each time. We're not just including that sets. It's just that most of the weight that's focused within the model is going to be on or near that particular quantile. So that's why you're going to get different outcomes as you go across. Now, there's a whole other area that I'm not going to get into in terms of properties, in terms of endogeneity, and things get a little bit strange in those areas that you have to be very careful about. I won't be discussing them, but you would need to make sure that it's meeting the proper conditions in that case. So I'm not going to say you can't, but it sounds like you could, as long as you did make some upfront, discussion about, possible endogeneity and what might be going on. And also remember that depending on how your primary data is set up, one of the things is this needs a large N. That's the only time it works. We need that large N to help us with some of the properties, especially when it comes to the being able to say something about, okay, I won't get into that. Just know that you need the long N. I'm trying to stay away from that theory as much as possible just to make it straightforward. Okay, so just keep that in mind. So, like I said, even though they're different, just make sure that when you're discussing it, you can make the comparison just by keeping that up front, that you have an OLS that has a particular objective function. You have the objective function of the quantile, but if you're actually comparing partial effects at the averages or average partial effects, we can kind of, in some ways, make a comparison, but it's not going to be a perfect comparison. Okay. And this is what I mean by the objective function. Basically, from our old version that we had before, we have a particular model where we're basically weighting the points that are above versus the points that are below the particular quantile that we're conditioning upon. Okay. This is what, when I refer to a linear program, this is basically what your computer is trying to minimize in the absolute value, or in the absolute outcome. So it's not, this is what I mean by it's a different objective function. It's, there's just a few things that we have to keep track of in here, but this is not differentiable. Calculus is out the door. We can't use it. Okay. This is also not a smooth function. That's a little bit of a problem for us as well. There's a whole field in terms of trying to figure out ways of smoothing this to make it more something closer that we could push towards, what we think of as smooth objective function. This is not in any way, but there's, like I said, there's methods that basically modify this to allow or try to use spline type methods to create something that's a little bit smoother. Okay. We can also put it down to something that's a little bit more straightforward. This might be how, I just wanted to show you the different ways you might see it, but they actually represent the same thing. Basically, we have a check-loss function in terms of basically when we're giving certain weights to whenever we have the error over our particular tau versus whenever we're below our particular tau. And when we're thinking about this, the asymmetric, it's going to be asymmetric around zero. So at zero, in this case, when I say zero, I mean the median. The check function is basically, in some ways, symmetric in the sense that equal weight is applied to above and below. As it moves, that weight structure gets changed. Okay, because it's actually, once we go to the 60th, we're actually weighting in a different way for those observations below versus above. So that's why it's symmetric around 0.5, but once we actually get away from 0.5, we're going to start basically seeing differences. So basically at any other quantile besides the median, the loss function becomes asymmetric. And at tau, say, as it approaches 0 or 1, that asymmetry changes. That's not what we see in the OLS. We think about that as being symmetric. And we're looking at logit, we're thinking about that as being symmetric. Here we have something that's asymmetric. So basically assigns different weights to positive and negative residuals based on that quantile function that we were looking at here. And allows us to focus on different parts of the distribution. But it's that localized versions of it. I just want to give you a picture of sort of how we think about this. So this would be the nice OLS. This is how we sort of see these quantiles for the tau equal to 25 versus tau equal to the median versus the 75th. You can see that, on this side for the 75th, and we're on that portion, that we're giving less weight on this side versus on the right side. And then as we're coming down the other way, we're going to start giving, on 25, we're giving more weight on this side versus on that side. This is what we mean by asymmetric. We're reweighting on how we're looking at these points around each of the quantiles we're looking at. This isn't important. It's just basically saying that there is something that's similar at the median, but after we get away from that, we're no longer in a symmetric world. So just some additional comments. So the objective function, like I said, is not differentiable, but under most standard regulatory conditions, basically this is always just meaning if our data in some ways meets what we refer to as well-behaved in some ways, basically we can say that it's asymptotically normal. We can use the linear programming. I wouldn't advise doing that by hand. There's programs that are designed for that. But there's algorithms that sort of change how we look at this. These algorithms are different tweaks on how we go about doing the linear programming. There shouldn't be too huge differences, but there can be differences on how they converge. Okay? So that's why we typically want to look at multiple, not just one way of estimating this. And then the standard errors, please let the program do it. Don't do it. But there's ways of actually formulating those. There's a sandwich Powell estimator, and there's the bootstrap. Most of what I usually see is looking at the bootstrap. Now, I just want to give you an idea of how this might be good for you in some ways or bad for you in some ways. So remember I was talking about the log when we do that, the Jensen's inequality problem. So a lot of times when we're looking at this, sometimes we can write out this function in this format. But if we actually take the log of our left-hand side variable, what would happen here is that basically this exponential would fall out and we would be left with this outcome. Now this is an oversimplification here because I don't have error terms or stuff like that. But the point is that this I can jump back and forth between. When it comes to the log though, I cannot do that way. Because by doing it in this format, basically, when I take the log, I'm not reordering the outcome. And because of that, the way it works, that because I'm not reordering, then I have no trouble converting back and forth between, wages versus log wages. So that is one of those good things in terms of the, basically it should be invariant to monotonic transformations. In this case, the log is one of those. I never went through in how we actually convert from going from the log to wages and some of the assumptions we have to make, but if you look in any Wooldridge textbook, you would actually see it's a little bit of a complicated process to get to that. And it's always considered an approximation given what your assumptions are. So just to give you an idea, I'm not going to go in a lot of the background in this case, but if we're actually looking at different quantile regressions and then their linear predictions, you can see where this is the median, or hold on, is this the median or the... Actually, that might be the mean, and then these are the different varied outcomes from the 25th, 50th, 75th, and I might have put the 10th and the 9th in there. But the problem is what you're seeing different effects along each of the outcomes across where you're at in that distribution. It's no longer, like I said, there's one effect, but there's varied effects over where you're at in that position. But let me be clear. Position within the conditional, not the unconditional. If we were to actually want to compare what we get in terms of the OLS versus what we get across the 10th, 25th, 50th, 75th, and 90th percentile, quantiles, basically what we're seeing here is we have a mean effect of 0.485. This data set, is coming from food expenditures, income's effects on food expenditures. It comes from Ingalls data sets that I pulled out of the quantile regression, or the quant reg package. And what we're picking up here is that at the 10th percentile, we find that our conditional effect is lower than what we find in terms of the OLS. 25th, basically, as we go across those quantiles, what we're getting is a larger and larger effect going across the conditional distribution. So what it's basically telling us is that as we move across the conditional distribution, our overall effect of, I'm focused on the wrong one, sorry. I'm looking at the intercept. 147 for the income. Actually, at the 10th percentile, we see a larger effect of income on food expenditures. But as we move across the conditional distribution, we're actually getting smaller and smaller effects, which we would actually expect. Food expenditure shares within any family's expenditures basically gets lower as they get higher and higher incomes. Basically, it's something we find quite regularly. So we'd expect the effects to also fall across income to the food expenditures. Okay? Oh, am I reading that right? Hold on. Yeah, so the overall share of food expenditures should fall as I'm at a higher and higher income. No, sorry, it becomes a smaller and smaller share as my income rises. Maybe just knowing income might not be enough information to get me a good result. Like remember to isolate, the more covariates we have, the better we can isolate the effects, right? So what if there's a shift at that point that goes from people who are actually earning wages to where there's their actual family income? What if that's what it's all being put in there? I'd have to actually go further into the data set and look back at the example to know why there might be that change. But for now, that would be the only guess that I could get out of my head. But again, like I said, it's good to go through this just as an example, just to see that what we're getting is some type of varied difference across the outcomes. You know, it's not just one mean effect. Now we're seeing differences at different portions of the conditional distribution. That it's heterogeneous in some way. So this gives you a better idea of what's going on in terms of this is the mean effect. And then we see that the effect is rising for the conditional effect of income is rising across the effects on the food expenditures across the conditional distribution. Okay, so in that case, it's just giving us a little bit more information. Again, like I said, it's not saying one is better than the other. There's a lot of assumptions that go into the quintile regression, a lot more that go into what we see in terms of the OLS. So if we're making that comparison, we can't say one is better than the other. I just want to make that clear that, you know, just because you're getting that information, there are more assumptions going into the quintile regression. Okay? When it comes to what we're actually seeing, remember the whole thing about heteroscedasticity that we were looking at before? What we're actually picking up, one of the things that the way some people describe this or try to talk about it is the fact that what we're actually picking up is the heteroscedasticity, the relationship that we actually are picking up between, we're getting more noise. So what's happening is, because this is localized, we're actually still have that noise, but because it's localized, we're getting a better effect, and we might actually picking up that heteroscedasticity. There are others that basically say that that's a bad way to interpret. That's why I said the field is sort of, you know, going back and forth and how we think about it. But heteroscedasticity is one of the ways we can think about how we're viewing that relationship between the predictors and the response. And the mean, we want to get rid of it so that we can get the best estimates. But in the quintile, we want that noise at that particular location to pick up a difference in response. That's probably a generalized way of saying it, but it might help you with intuition. So basically, we're picking up, you know, it leads to misleading inference in the OLS, but with the CRE, we don't assume constant variance. So it's basically robust to that heteroscedasticity, but it's also helping us to pick up the fact that we're getting a different effect at that point. Okay? So in that case, the CQR uses weighted absolute deviation. That's sort of what we're saying with the objective function, making it less sensitive to that error variance structure. And then each quintile is estimated separately, so different parts of the distribution can have different slopes in the variance, because if the variance is changing with the predictors, it's that localized effect. Potentially different slopes at different quintiles, revealing how the heteroscedasticity manifests. In fact, whenever they were first actually doing this model, that was the thing. They were trying to model the heteroscedasticity. Now we use it as ways of seeing how the effects might change across the conditional distribution. Just to, you know, it's how you go about that intuition. Okay? So interactions can become a little bit more difficult in trying to discuss this because remember that it's not an interaction of a global effect. It's an interaction within that particular localized effect. So basically, we'd include the product just like we did with the OLS. And then in some ways, we're looking at that beta 3 in this case, shows how the slope of the x1 with respect to y changes with the x2 at that quantile. Now imagine if I do 99 quantiles with interactions. And x2 in this case, is continuous. Imagine the number of results that I get. It becomes a little bit hectic to kind of go about, right? So you always keep in mind that you need to figure out a way of generalizing some of these results. So you can use interactions, but you need to find a way to show it in a interesting way that doesn't overcomplicate that problem. Okay? Because like I said, as many quantiles you estimate, that's how many each betas of these 3 here you get. Then when you add that interaction, if you're trying to look at that variation over the x2, then it's getting even more complicated. Looks like it's about to really storm out there. Okay, so just keep that in mind as we're going through. And the effect can differ across quantiles. So basically, it can be positive at the lower and negative at the upper quantiles. There are a few assumptions that I'm kind of skipping over, which if you try to use this, you would kind of go through and try to be a little bit more clear about it. But there's some, assumptions about overlapping. Quantiles can't overlap. There's some assumptions there, but given the way we estimate it, that rule sort of breaks down. But I'll let you kind of go into that on your own. So why it matters. So if the variance changes across the distribution, an interaction might be irrelevant for the median, but it becomes crucial maybe at one of the upper or lower tails. Okay? So the interaction that you're looking at that you're hoping would help you with your question of research might be, meaningless at the mean. But at the tails, it might become a little bit more important. Okay? And then QR allows us to see those interactions that are more pronounced at certain levels of Y. And sorry, I should have put that. At certain levels of the conditional dependent, in this case, conditional Y. I'm trying to be very careful in how I discuss it. So just so that we're not staying kind of late, again, I have a practical here we can kind of go through. And basically what you're going to use is the wage pan data from the Wooldridge. Now this is a panel data set. For right now, we're going to assume that that structure doesn't really exist. I'm going to basically take it down. Oh, hold on. I have to fix my slides again. Or I'm going to be missing half of the, I think there's a beta 7 and beta 8. So basically once I fix that, I'm basically going to ask you to do an OLS estimation of that outcome. But what I'm going to ask you to do is I want you to compute the robust standard errors. But I want you to also cluster on occupation. I'm just saying that the clustering could be by occupation level. I could be wrong, but this is just to show how you might go about this. So we're going to focus on that. The problem is that keep in mind that in this data set, I get a dummy variable, binary variable for occupation 1, 2, 3, 4, all the way to 9. Remember how I told you to create binary variables from categories? Now I'm going to ask you to put it back together. You take it apart, now you're going to put it back together. Then you're going to go through and bootstrap the standard errors. I didn't put it here, but you should be using the boot command. Don't do this on your own. And then also, I just want you to do a conditional quantile model for 10th, 25th, 50th, 75th, and 90th percentiles. And just do a visual result comparing to the coefficients on the key variables. Okay? This is just to go about, again, testing what you've already done before, doing LM results, changing and looking at the clustering. Basically just seeing different results across that for different clustering outcomes. Oh, sorry, robust versus cluster versus bootstrap. and then giving you an idea of how to run the quantile regression. Okay? It's not tested or anything. Just put in some effort to help, go about the programming side of it. Okay? And then I have a few references. So one of the ones I wanted to point out to you here is, so if you plan on using quantile regressions, make sure you read this paper. He basically goes into pointing out all the mistakes that were basically present in a paper that was supposed to be, ahead of its time on development, and basically points out all the things, the way they were discussing it, the way they were trying to compare. It shows you all the errors that you can be making because we're so used to talking about results the way we do with OLS that they sort of applying those to quantile regressions. That can be problematic because it's just a different way to discuss it. So if you're actually going to use these methods, that is one of the papers you could read to sort of get a good background on how to discuss how the intuition works before going into any of the theory, any of the attempts to actually run those models. Okay? And I'm also big on that because in 2020 and 21, when I was trying to do the same type results, I made all the mistakes that they were pointing out were wrong. Because I am so used to talking about this as in terms of OLS, in terms of other types of models that we look at it and compare the average treatment, or not the average partial effects. We're so used to doing that way. It can't be done or discussed in the same way. It just needs a bit of a tweak on it. So if you really go that route, that's a good paper to read. There are more, but it's just one that it's an easy read. It does a good comparison and actually compares to what the published paper was and saying that, this isn't exactly correct. This is completely wrong. This is how it should have been discussed. And that can help you in terms of how you go about your research if you use it. Okay?